All right, this title of this video totally fit on this page, no problems. We're going to talk about domain. We've talked about domain before, but we're going to talk about it again. Vertical asymptotes, again, we've talked about. And removable discontinuities, we haven't talked about yet, but removable discontinuities are basically holes. Kind of like there's almost a little hole in this line right there. Okay, so let's remember what you probably have been taught, but may or may not remember. The domain of a rational function. The domain of a rational function, and again, let's call this rational function the same thing we did earlier. Let's call it r of x, and it's just one polynomial divided by another polynomial function. Okay, that is what a rational function means. Polynomial divided by polynomial. And polynomials, again, are just a bunch of power functions added up together. So it's what we always do in math, right? We always say a definition in terms of a previous definition, which means that math either makes a lot of sense for building on top of itself, or it makes no sense if you forget anything, because we always refer to other things. Okay, so this domain is the set of all x values such that the denominator q of x is not equal to 0. Now, if you don't remember set builder notation, or if you haven't seen this in a while, this basically just means everywhere the denominator isn't 0. It's okay if you just use interval notation instead of this set builder notation. Okay, so all you have to do to find the domain is find when the bottom equals 0 and throw those out. Remember, domain is just the set of all the values that you can plug in, the set of all x values, the set of all acceptable values to put into this function. Well, let's do some problems. Example 2. Find the domain of these rational functions. F of x equals x plus 3 over x squared minus 9. So notice, to find the domain, it literally doesn't matter what the top is. P of x doesn't matter. The numerator doesn't matter. The only thing that matters is saying, when is the denominator equal to 0? We can't plug those values in. So let's find when the bottom is 0. Let's find when that denominator is equal to 0. And our domain is going to be everything except for that. So the denominator equals 0 when x squared minus 9 equals 0. And you can solve this either by factoring or with the square root property. Adding 9 to both sides, taking the plus or minus square root. Square root property, a lot of people forget that plus or minus, so let's factor for practice. This is the difference of squares, and it factors to x minus 3, x plus 3. So now we can use what's called the principle of zero products and say that this is equal to 0 and each piece equals 0, right? If x is equal to 3, then this whole thing is 0, because we're multiplying 0 times something else. So this is when the denominator is equal to 0. We can plug in everything except these numbers. You try to plug in 3 or negative 3, you're going to divide by 0. That's a no-go in math. Dividing by 0, bad. Okay, so our domain is everything except for this. So our domain is everything, all real numbers, except these. You can write this in interval or set builder notation. In interval notation, it's all the numbers from negative infinity up to 3. And that's a union sign, all the numbers from negative 3 to positive 3. And all the numbers from positive 3 to positive infinity. Literally everything except negative 3 and positive 3. That's why I have parentheses. Parentheses because 3 and negative 3 aren't included. Or you could write it as a set of all x such that x is not equal to positive or negative 3, which I think is a little easier to write. Technically, it's a set of all x in the real numbers, but we're fine writing it like this for now. That's how you find domain. Let's do another one for practice. Part B. Y equals x plus 1 divided by x plus 1 times x minus 2. Now be very careful here. You might want to cancel. I want to cancel, but we can't cancel here. We'll talk about why we can't cancel right after this problem. But in the meantime, just take my word for it. And again, our domain is going to be everywhere except when the denominator equals 0. So the denominator equals 0. Well, we don't even have to factor this one. It's already factored. When x is equal to -1 or positive 2. So these are the only values we cannot plug in. If we try to plug this into our function, we're going to get something that's undefined. So we're going to say our domain is, again, -infinity up to -1, union -1 to positive 2, union positive 2. I hate interval notation for stuff like this. It takes so long. Or the set of all x such that x is not equal to -1 or positive 2. Again, you do not have to use both. You can use either. You can pick one. I like this. But just because I like something doesn't mean you have to like something. I think I tried to get out of that phase around kindergarten or something. Okay, so that's domain. Now let's look at these functions. Because these functions, we can visually talk about the domain. And not only can we visually talk about the domain, but there's going to be some little differences between them. Okay, so if we look at these functions, first one is x plus 3 divided by x squared minus 9. And what was our domain? We said our domain of this function was everything except for positive 3 and negative 3. Okay, positive 3, that makes sense. There's a vertical asymptote here. Right, there's a vertical asymptote at x equals positive 3. Why can't we plug in negative 3? It looks just fine, right? Negative 3 is just... Oh. There's a hole right here in the graph. We can plug in everything around negative 3. But negative 3 itself is not defined, because if you look at this function and plug in negative 3, you're going to get 0 divided by 0. So in this case, there's a hole at the point negative 3, comma, hold on, negative a sixth. Is that right? Yeah, so there's a hole right here in this graph. So this is what the graph actually looks like. This is what's known as a removable discontinuity. Okay. Removable discontinuity means that if we wanted to, we could create a piecewise function and essentially fill in this hole, and it'd be continuous. There's no way to modify this function quickly to make it continuous here. We haven't really talked too much about continuity, but continuity just means it's all connected. You don't have to pick up your pen or your pencil while graphing it. There's no way to connect this vertical asymptote. But this problem is much more fixable than this one. That's what removable discontinuity is all about. So in our domain, if the denominator equals 0, sometimes that'll have to do with a vertical asymptote. And sometimes it's going to have to do with a hole. We're going to talk about which case is which. That's going to be done. Not yet. Nope. Yes, yet. We already did part B. I thought we finished part B for a second. All right. So there's two types of discontinuities. Discontinuities. And again, these discontinuities are the points outside of the domain, right? So when the denominator equals 0. So when we're finding the domain, we're also finding the discontinuities. The domain of a rational function is going to be all real numbers except a couple points. And at those points, we'll have two types. Okay. So let's suppose that q of x is our denominator polynomial function. Suppose q of x has a factor of x minus a. Well then, if p of x also has that factor, what's going to happen? What are we talking about? Let's say the denominator has a factor. So this denominator has a factor of x minus 3 and x plus 3. Let's look at the x plus 3 case. That's what we're talking about first. If the top has the same factor as the bottom, then that 0, that's the 0 of x equals negative 3. What happened? That x equals negative 3 was a whole, a removable discontinuity. So if they both have that factor, there's a removable discontinuity right there. Again, colloquially, this is called a hole. So in our first example, there was a hole at negative 3. How did I find the y value? Remember I said the y value was negative 6 for this hole? We found it using limits. But that's finding that y value is a little, well, you can also kind of find it if you want. If you cancel this, then that gets rid of the hole. That's why we can't cancel it. Getting rid of the hole changes the function. But if we did cancel it, that would tell us what the function would look like without the hole. So if you cancel it, you can find the y value of the hole. Okay. So if the top does not have that factor, then x equals a is a vertical asymptote. And a lot of times I'll abbreviate vertical asymptote VA. So that's what this video is all about. Domain is just everywhere the denominator is not 0. And if the denominator ever is equal to 0, we either have a removable discontinuity, or a hole, or a vertical asymptote. And that's how everything in this video ties together. Do one last example. Example 3. Find the vertical asymptote and removable discontinuities of the functions in example 2. All right, so that first function, we graphed the first function. We should know the answer already, but I want to use this property and do it more formally. All right, so this function from example 2a was right here. So we always have to factor, right? To identify which one's which, look, factor. We have to know their factors. Need to know the factors here. So let's factor it. This is going to be x plus 3 divided by x minus 3. X plus 3, and again, don't cancel. Canceling changes the function. It fills in any holes. So there's two candidates, right? X equals 3 is going to be one candidate, one kind of discontinuity, and x equals negative 3 is going to be another type of discontinuity. As a side note, remember that they're flipped. So the factor has x minus 3. That correlates to a 0, or sorry. Yeah, to a 0 at x equals 3 for a polynomial. So make sure to keep them straight. So this one does not share a factor, right? Does not share a factor. Or does not, let's phrase it this way, does not appear in the numerator. Whereas the second one, this factor does appear in the numerator. So if it doesn't appear in the numerator, then we have a vertical asymptote. So this first one is a vertical asymptote. And since the second one does also appear, it would cancel if we tried to, and that would be a removable discontinuity, a hole. And that's how you classify them. And that's what this problem wanted us to do. We could also have done this for part B, which was y equals x plus 1 over x plus 1, x minus 2. And again, there's two kinds of discontinuities here at -1 and +2. -1, it does share a factor. It should be a hole. A removable discontinuity. The second one does not appear in the numerator. It does not share a factor, so it should be a vertical asymptote. Let's check our answer for part B. All right. So part B is looking at the function. Whoa, I hate it. I do not like it when Desmos does that. It's going to be x plus 1 divided by x plus 1, x minus 2. There should be, let's check, see what we have. Should be a removable discontinuity at -1. If you look at -1, yep, removable discontinuity. And there should be a vertical asymptote at x equals 2. And yep, there's indeed a vertical asymptote right here. There we go. That's how the domain, the vertical asymptotes, and removable discontinuities are all connected. Let me know if you have any questions, and good luck.